Hi, everybody. Thanks for joining this session. I'm going to discuss explainable AI for large language models. And I have shared a collab. So the link is in the chat comments, and it's pinned. And I suggest you just follow along with what I'm showing on the screen. It's kind of redundant to have both. And sometimes running them and as I'm talking is actually distracting to you, not to me obviously, but it's a lot easier to just see what I'm on the screen, and the code is for later, so you can run it yourself if you like, or go back and kind of review something if you're so inclined. So I'm as explained what's the contents of this. I'll run the first few cells because those are the ones that take amongst the longest to load. Yeah, so basically this is boils down to, like, here's the table of contents, you have preparations, and so what I'm doing right now is installing the libraries, loading the libraries, then loading the large language model, which is Llama 2. I know there's a 3, but they keep getting bigger, so it becomes more challenging to share these techniques without, like, even more resources, in terms of GPUs and so forth. Then we go to the main section, and main section is first I'll discuss quickly what is Llama 2. Obviously, it's a large language model, but I'll go a little bit beyond that, and then how to visualize attention scores with BERTviz, and then feature importance with SHAP. If there is enough time, it's not something that's in there, but I thought we could look into Captain, and Captain has some really cool techniques for uh, also for deep learning. Mostly, like, I use it myself for a lot of computer vision applications, but you can also apply them to language models. So we'll look at that if there's time. Otherwise, the only way, I mean, if you have the link, so you'll be able to run it. Um, so right now, what it's downloading the model. It's quite big, but thankfully this does it quite quickly. You know, what's 13 gigs. So I'll now skip ahead while it's doing that to what is Llama 2, or Llama 2, whatever you want to call it. And it's a family of pre-trained transformers, fine-tuned, in size somewhere between 7 billion to 70 billion parameters. Like most large language models used to generate text, it's a decoder only. In other words, an autoregressive model, which means at its core, it is really true what they say, which these models were trained pretty much to just predict the next token. And I'll explain the subtlety and differences, and you'll notice what they really are between what a token is a word. You say word, but really we mean token. And based on understanding how words follow and precede each other. So that's what they're trained to do, and they can do a bunch of downstream tasks basically based on that. So you could use a large language model to cluster text, classify text, to do all sorts of, answer questions, obviously, do a lot of other things, just because they know what order words are to each other. Kind of sounds kind of silly, but that's the foundation of everything. Obviously, like, encoder decoders are uh, have the same component. They have a decoder, but they also have an encoder. And one of the things they can do, and they're specialized in, is in translation. And they can do question answers too, because you pretty much have two pairs of text, and one relates to another. So basically, it's learning how to pair these two together. So it can be used was traditionally used for translation, and it can be used for a bunch of other things, as it says, question answer. But then again, the decoder can be used for question answering on its own. Um, so and then the encoder, like, was the first one that came out that people started to pay a lot of attention to, which were the BERT models. And so all the BERT, different kinds of BERTs. Roberta, Distilbert, and so forth were used for all these different tasks. So they're very good classifiers, and they do other things as well, but it's much more limited than what a decoder can do. So this workshop has 3 sections. Each one has a different purpose. One is visualizing attention, and that's a good like starter because that you get a grasp of what attention is. In other words, what makes a transformer tick, and in particular with the problem, what makes it tick for that problem, right? Second, we dive into feature attributions. So what matters the most to the large language model? Obviously, in the context of a question, and its prospective answer. And third, we look into feature ablations. And what happens if we switch words around? And that has a very deep meaning to it because that also relates to the causal understanding of language, counterfactuals, and all that. So first, I said, what is attention? This section. So we'll get to that in a second. First, we're gonna run through a simple prompt. So where was the actor that played Marty McFly in Back to the Future born? It's a very simple question, and you would imagine maybe it's not so well known that necessarily it's like obvious, but if for a large language model that was pretty much trained on the Wikipedia and a bunch of other things, it probably should know that. Um, then we're gonna get we're actually gonna run it through the model, and so we're gonna also and this is very important. We're setting the max length to 80. So this in other words, we pretty much don't want an output that's more than 80 for this particular prompt. But more importantly, let's look into the inner mechanics of the model because that's very important. So if we print these over here, you can see what all this is. And if you go to the paper about this model, it will tell you what the architecture is anyway. But it's basically a bunch of different building blocks. The more important things to know about this, and you can see them right here, is the embedding size. So you see 32,000, and that's the size of the vocabulary. So that's a number of different tokens that can be represented by the input IDs. And we'll see what the input IDs are in a second, but so that's basically what is used to call the model once represented as numbers. And then the context length is, and you've probably heard this before, is defines the number of tokens the language model can process at once. So in other words, how long can your prompt be? And mind you, the prompt is not necessarily just a question you ask. There in a large language model, in many applications, it's far more than that. It includes a lot of like directives or system prompts that are used to kind of direct what kind of wage, in what kind of format it should output the responses, what should I do with different cases, and what kind of tooling it has available. There's a bunch of different things. Um, it's like the memory or attention span of the model, and it's usually not a lot. It is even these days, while they talk about a million, it might not be a lot for a lot of cases. Um, and then attention, hence, it defines a number of heads focusing on different parts of the sentence or different types of relationship. And it provides a very comprehensive understanding. And you can see that here. These are the attention heads. So if we look at this, right, this is the traditional like transformer architecture in the very first like paper. So you got the encoder and decoder. So this is just the decoder part, and you zoom in, and this is basically what's here, except for one of these because it's not connected to the encoder in this case. So it's like the disconnected part of the machine, and obviously it has some special sauce. It's been many years since the original decoder came about, so there's like some new things that this includes, but they're basically the same building blocks. There's normalization. There's also a feed forward part, and there's this attention mechanism. And this in particular is what's called a group multi-query attention. So it's a specialized attention mechanism that is proved to be more effective. So here we can actually output this, and we'll pretty much, by what was outputted in the tension matrix, we can tell, by the dimensions of it, how many heads there are. So you don't even have to look into the paper. You don't have to even look here. It's just the output of the tension, because we asked it. I forgot to mention that we asked it here to output the tensions. We can, by accessing this, we can reach that information. So you wonder what all these numbers mean. So basically there's 32 heads, and each head has a 19 times 19 matrix, since there are 19 tokens in the input. So remember, this was the input, and there's 19 tokens in here. There aren't 19 words, but there are 19 tokens. And we'll see those in a second. And when I was talking about input IDs, you wonder, well, what are those? Well, the input IDs are the tokens turned into numbers. So each one of these numbers represents one of those tokens. And if we want to see what the tokens are, we can then use this convert IDs to tokens, and I'll convert them back. Oh, oops. I get there. So this is it. And as you can see, not all these are entire words. In fact, my fly is made up of 3 tokens. And the question mark is a token. And then there's an extra token at the beginning, which just denotes it's the start of it. So that's pretty much the way it turns out. So now we're gonna visualize attention patterns, so you get a grasp of how attention is working in this model. And it takes interpretation. It's not like it's necessarily gonna tell you, okay, this is what's going on, because it's a very complicated machine, and sometimes it isn't that obvious. But it's just a question of going through a number of these and seeing patterns. And granted, it can be kind of tough to look at this view and see that, especially for these very large ones. It's a hell of a lot easier when you have a smaller model, like a BERT model that was used for classifying or something like that, because it can become obvious. Okay, this is why this word is picking up here. Or even in a translation model, you'll clearly see what words are translating to others, right? And what they call a sequence to sequence one. So it takes a bit to load there. So what are all these? So these are the layers, and I forgot to mention, actually, this is not written correctly. There are 32 heads, and um, which with 32 layers. So 32 heads and 32 layers. So one of the advantages of having a lot of heads, it actually makes it less dense, so it's not processing everything at the same time. The other advantage is actually not only during training, but during inference, it can be parallelized more easily. So it has a huge advantage in speed. Um, So sometimes, as I said, it's not as obvious. A lot of these things end up going towards the start, because it's basically, that's like the default. But you start to see how there are connections to different words. And so, as I said, this is a model that's meant to predict the next word. So you can tell what that means, in the sense that words that are related to each other, they're the ones that are connected. And words that follow each other are naturally connected too, especially when they have oh, something happened here. I don't know. Maybe I clicked on something. Okay. So they're naturally connected to each other. And perhaps like a better visualization is this one I'm going to show you right now. So it becomes more obvious when you have like a sentence A and a sentence B, but that's not the case here because the training data was a single a single corpus that wasn't connected to any other corpus but itself. So it's the idea, it wasn't like, oh, here are the questions and here are the answers. No, it's the questions followed, the answers follow the questions. So that's how they're connected. And so this is a case where you have, and it becomes more intuitive, where you have a question and you have an answer. So you can see how it's connected in the sense that, well, robot is here and obviously it's in the answer, but also certain words pertain to robot. So human and robot are, might be uttered in the same kind of context often. Obey might be often connected. And there's certain words, verbs that are related to subjects and objects and so forth. So you start to see those connections. This is this kind of of uh, large of attention mechanism in which you have self-attention. So you what you see is that words are clustered with each other. So like let's go here to a particular layer, and I don't know, for some reason the head isn't showing up, but let's just do it for this head because it's supposed to show heads and layers. So you have 32 of 32. And so what I do here is I'm like, okay, well, these are the words that are connected to actor. So played obviously has a strong connection to actor, and then Back to the Future, back by itself not, but in a as a kind of cluster of words, yeah, it makes sense. And muck is generally like something that it could be, connected to McDonald's. It could be connected to a bunch of different things. It seems to be crashing for some reason. But hopefully you get the picture. And the picture is that attention is all about creating these relationships. And they're naturally called attention because attention is something that doesn't exist in an island. It exists amongst a series of entities that we connect. So when you pay attention to one thing, you're paying attention to other things that are connected to it. So a good thing about this mechanism is that it allows in a much more sparse manner to make these isolated connections between entities in a very efficient manner. So and part of the efficiency is the use of tokens. So there's a token for every there's a token for ly, and you can think of y. There's a token for ly. Ly is a common ending for a lot of words, right? There's a token for MC. MC is a common beginning to a lot of proper names, of surnames, right? And F, there's a token for every letter in the alphabet. So, but there's lots of words that are very common, like where, was, that have their token. And obviously punctuation is another one that has these tokens. So that's part of the efficiency as well. Like obviously if we were to create tokens for every single word ever uttered, instead of 32,000, we have, 32 million easily. Right? So that wouldn't be efficient at all. So I think we've devoted enough to attention, and I don't want to have enough time to go into SHAP. So this is this is basically what we did there. We didn't quite get the output. So I'm showing you like by using the command generate, we can generate the output. One thing is to pass the input and just for the sole purpose of getting the attention matrix. Another one is, okay, give me the output. And that's what this is doing. And so it's also what we're going to do next with the CHAP. And so CHAP is a it's a method for explainable AI. And one of the advantages CHAP has, it's based loosely on Shapley values, which are based on game theory. And the idea is that if we see each feature, like in this analogy I like to use, each feature as a player, like, and in this case, each token is a feature as a player, and we can't, how do we assess how important a player is in the game? You know, it's not done in isolation because a player plays with other players. In the same way words work together. You know, it's not a single word in this prompt that is doing all the work. It's the collection of words, and sometimes a few in tandem that make it work. So if we see what words here were the ones that made that response happen, they're not all doing the effort. We could probably take in all the ins, all the tos, all the does, even the that, and it still would work, right? So like SHAP, if we're using SHAP for feature importance, and you can use it for different things, but basically it's finding its attributions, and that's a common term we use in explainable AI. It's a we attribute features output to the features. So those values can be used to assess a lot of different things, and one of them is feature importance. So that's basically a ranking of which features had the biggest impact on the output. So here we're going to do that. We're going to run it, and so what it's going to do here, it's first going to train a surrogate model to connect the input and the output. Then it's going to calculate based on that, on the outputs of that surrogate model. It's going to create an explanation using the Shapley method. So when I said it was loosely related to the game theory, it still tries to adhere to a lot of the principles, and that's one of the criticisms they have on Shap. It doesn't adhere completely, so it's not as mathematically sound as the original, because it would be computationally impossible in many cases to create all the different combinations. So if you think of all the different combinations of words in the input, the ways it could be arranged or replaced by something else, by a different token, it would be like impossible to find to be able to assess every single combination. So we go back to the game theory analogy, and I was talking about, like, say we had all the players in the basketball court, and we came up with a basketball game where we have 19 different players, each representing one of the tokens, and we tried to say, okay, we're going to make coalitions of these players, and we don't want to use all the 19 players on the court. We're just going to use, I don't know, 5, 6 at a time, and over time we get a sense of which ones are the best ones, which players are the ones that produce the best outcome, right? And like all those different combinations would be too many to actually make a proper assessment. But statistically, you could probably come up with a threshold that says, okay, this is good enough. And often that's what SHAP is doing. So when we look at the SHAP values, and I'm going to copy this because this is the original one, and I want to really it every time it runs is not necessarily the same. Like obviously, like this time it's assessing an output of 47 tokens, it's 49 tokens, and before it was at 47. So when you look at these numbers, the first number relates to the input, the second one to the output. So one of the good things about SHAP is that it doesn't create a single number for the features only, where it's saying, okay, this is how important your feature was, but this is how your feature relates to your output. So in many cases, the outputs are called observations because they're basically rows in a table, or maybe they're pixel values in an image that was generated. But in this case, they're other tokens. So and so basically what we're doing here is we're running all these different things. And so the SHAP values produce these numbers right here. But where the way CHAP usually works is with a different rearrangement of values. You got the observation first, and then you got the features. So one of the, I would say, bad things about these libraries is sometimes they don't adapt too easily to new kind of different kinds of data, new deep learning algorithms. So you have to kind of understand what's underneath the hood in these methods themselves to make some of the capabilities work. And this is one of those cases where I say, okay, well, this is actually the other way around. Like, I don't, first of all, I don't need this number, and that's one of the good reasons to kind of output this. So you get a sense of the dimension and say, well, I need to rearrange these two things. And so that's what I'm doing here. So basically, I took this number over here, I took this number out in both of them, and I rearranged these two numbers. So that's what I'm doing here. We're going to be soon out of time. And I don't know, I'll let you guys vote if you want to see the captain or you want questions. Because I don't think we'll have time to go to the captain. Um, so here's how do you calculate feature importance based on this? So imagine you have this matrix. You got 47 features, or 44, which represent the 47 features, the 47 tokens that were outputted. Those are the 47 observations. So you got the 47 numbers that represent the output, and the 19 numbers that represent the input, and you got them in a matrix. So if I want to see how much the input impacted the output, what would I do? I would just take the absolute value of all those numbers and then take the average across all the features. And this works for every single SHAP output, every single SHAP values. So whether you're using tabular data or you're using images or anything like that, you could do an average across features in a similar way. So what I end up with is this. And I might end up with a different thing. So that's why I want to run it twice. Well, I already ran it, but I'm going to run it again. So here, ooh, I didn't run this. I guess I didn't run this. That's what happens. I start skipping cells. Okay, so I'm running these, and I just want to show you how these things can vary in accordance to the output. So before actor had a higher importance than it does now, because it's going to depend on the output, which is why it's so important to run this several times. And then what I suggest is to averaging out the chat values, so you can get an accurate depiction across many different generations of text. What is the most important input? So is born tends to be always on top, but where, was in the top three. And by running this several times, which I have, I realized that where is obviously an important token. It, like if I replace that for what or when or something or who, I would get like a different answer. So yeah, of course it's going to be important. Um, so like this may seem like a silly exercise, but you could apply it to any kind of question, right? So you can optimize prompts based on this kind of workflow. And you can also debug the prompts. Why did you get like a weird response? Why didn't you get the response you were expecting? Why did it seem to kind of hang on a certain word you said? Like maybe it doesn't understand an expression. So there might be like interesting things you get from these sort of exercises. So another thing you could do, that's one way of visualizing, but as you can see here, it's kind of, it's they're not even in order. They're in order of importance, but I mean, you could obviously order it in the order they were, but it's still kind of not easy to kind of pick up, you know. So what's a nicer way of presenting those attributions? How about color coding the words? So I just want to be able to compare what I got before with what I got after. So, but it's fairly consistent. So I'm using this function over here, which I created to color code this, and you can see the intensity of the blue relates to how important that input was to produce whatever output it produced. But it's still doing it kind of disconnected from the output. So let's look at that for a second. And again, I'm just doing this to compare. Um, this is a nice little plot, but it can be very featured, very information dense, these plots that Chat does. So you kind of have to know what you're looking for. So here, if I go over muck, you see, well, how the certain inputs are most like connected to it, and you would expect that like over here, you go here to Marty, you would expect, oh, back to, and which one is this one? As I said, they're a bit hard to kind of relate. I don't quite particularly like this. It is kind of an interesting one, but it's not very easy to navigate. But like say I go to Canada here or Alberta, let's go to Canada. And of course it's going to relate to born. So born and Canada, this was the question, where was he born? You would expect born to be related, and then back. Let me see which other one. So just to kind of reiterate, I didn't properly explain this. This kind of chart is very common in chat, and it's called a force plot. I think that's what it's called, a force plot. And this has been adapted to this to text. But what it talks about are two forces. Basically, you got one force that is in favor of a certain feature having importance, and other ones that are kind of against. So you can think of it like of a certain, like a tug of war. So born is, and another thing that's kind of counterintuitive about this chart, personally, I think red kind of communicates something bad or negative, and blue is more like on the positive side. But here they kind of have it flipped. So red is a force in favor of something having a high attribution, and blue is against that. So a bit counterintuitive, but you can see which words relate. It's kind of hard to appreciate, but if you hover over them, it will connect you to the word. So this is the input and that's the output, and you can see which words connect to which. Obviously, if you look at these numbers, all of these will be connected to born, because that's the part precisely that answers that part of the question. So, and mind you, I asked where, and yet it still answered the number, with the date. Maybe I wasn't interested in the date, but it did that. So of course, when I go Canada and I go Alberta, born, 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 born. But when I go to parts of the words that relate to who he is, it's gonna go to actor, to McFly, to and the name. If we go to the name, that's a piece of information I did not provide. It's also going to connect it to, as you can see by the color coding, to all these different red and blue parts. In particular, played, Back to the Future, right? So hopefully that makes a bit sense. I realize this kind of plot is tricky, to say the least, but it's another way of seeing that. Now we have some minutes left. I'll let you guys vote if you want to see feature
Mm.
ablation with Captain, or
Yeah,
you want to ask
let's do it.
questions.
Let's do the last section too.
Okay, this one is kind of interesting. I'm not going to run each part of it because as you can see, sometimes I'm afraid it's just gonna change the outputs. And I want to explain it in context of these outputs that were, okay, so I put in this prompt. And if you put in any prompt that is not pretty much a question, it will fill in the blanks with what is left. So you don't even have to ask the question. So that's kind of cool because you can see into what it will fill. To you can assess things like biases, like tendencies to see things a certain way or kind of connect things a certain way, pretty much because of the way like the testing mechanism is connecting words to each other, right? So here I said, sorry to put you on the spot. Amir lives in Toronto and is a recovering quantum physicist. Well, that's what is in on his LinkedIn. His personal interests include, and let's see if they see this right, playing the guitar, reading science fiction, and watching obscure movies. I don't know if they got any of that.
I
Maybe
feel
not. I know
exposed.
he likes to hike. What? They got it
Right.
right?
That part is right.
Which one?
Yeah, I don't do any of these really. Sorry.
Okay. All right. So if I run it again, it's going to say a different thing, you know? So if I run it again, it's gonna, philosophy, meditation, and study of consciousness. Also,
Yes, this one is
that's,
right. It knows me.
yeah, okay. Also, I said max tokens is 15. So if I don't put max tokens, it's likely to gonna kind of come up with a, dissertation on who Amir is. And I don't want it to do that. Um, so so perturbation, we already looked at what a perturbation-based attribution is because that's what basically SHAP is. Um, But feature ablation works differently because it works with a baseline. It can be an arbitrary baseline. So imagine like having like a blank canvas, and you're comparing with the picture that came out, the output that came out to the blank canvas, right? So what that would that be? Generally, ablation would mean removing the token altogether. So if we're talking about an image, it would be okay. I'm just gonna take a piece of the image and I'm gonna replace it with a white block. So that's what ablation would mean in the context of an image. In the context of the text is removing the token altogether. So what happens to the output when I remove the token? Okay. Also, it could mean replacing the token because let's say the blank canvas is not a blank canvas. There's something there already. So that's kind of cool because you can compare a lot of different things. So here we can see which ones matter the most. So like if we're seeing in terms of token attribution, it's fairly intuitive to see that playing connects to include, physics include to connects to playing, or phys, um, and guitar to phys to a certain degree. Recover is actually negatively connected to playing. I don't know why. Um, but and watching obscure is seems to be connected to a certain degree with recover. No, obscure with recover. That's that's a weird kind of connection there. And Toronto to playing to science and to obscure. I don't know why Toronto has this connection to obscure, but maybe popular. There's some kind of connection there that I'm unaware of. But that's like a very general attribution that's based on just removing the token, and that's not very kind of that doesn't make it would render a lot of things um, kind of counterintuitive or not counterintuitive, just simply nonsensical. And that's something that we have to be very careful with explainable AI methods, in particular those that do um, perturbations. Because if you're testing a perturbation and it renders your data nonsensical, it will go to a place that the large language model wasn't trained to do, you know, because amongst the billions of items that were used to train this large language model, there weren't a lot of items that had English that simply, had all the, words the and to and, just seemed like a bunch of gibberish. It's likely it didn't happen a lot of times. So it might not have the capabilities to understand that as well, right? It might fill in the blanks, but what does it mean to have a sentence without a verb, you know, or without a subject, and will it make sense of it? Because that's what happens when it's doing this. It's so that's not a very good way of doing it. And so here we're like, okay, let's just remove these words. I'm just interested in removing the name and removing the city and removing these individual words one at a time and seeing how it connects to the output. And so this is what happens. It pops out a lot more. The colors are more intense because obviously it's making more sense what it's doing here. It's just not removing random words, because of course if it removes is, us, that, it's not going to make a lot of sense to do that, because in many cases some words are the ones that make the word have meaning, and others are just the glue. So we're starting to get there. We're starting to see these words. Okay, yeah, Toronto seems to have this connection with movies, with obscure, Amir with watching. There might be some novel out there called Amir Watching, or I don't know, or something like that. I don't know. It is negatively correlated with science. I don't know why. With plane, he is, and then his is connected with science. There we see an instance of bias, of gender bias, um, but we're not sure because it's just is is it his against her, or is it his against nothing? And that's the case right here. So we can confirm that only if we replace his with her. Um, and so that's what we're going to do next. We're going to use a different baseline. And so the baseline we're going to use is, Julia instead of Amir, Vancouver instead of Toronto. Hopefully there isn't like a huge like how do you call it, beef going on between Toronto and Vancouver. But recovering versus successful, quantum physicist versus AI entrepreneur, you know, and then his versus her, right? So let's see what happens when we replace these words like one by one, right? And then yeah, we do confirm like the gender bias, and it's even worse than we thought, because his is much more attributed to playing the guitar than her, reading and science as well, and movies, and obscure is a little bit in the opposite end, right? And we can start to see some other things emerge. Toronto, also in connected to watching and obscure, and so like, but this is not very, what's the word? It's not very thorough. We can go even more thorough if we throw in more things in the baselines. What happens if we try different baselines? You know, what happens if we throw in different cities? Like, just not try Vancouver, let's try Calgary, let's try Montreal, and see if there is really, like, amongst Canadian cities, Toronto is the most obscure of them all, right? And what if, like, we have more than one his and one more than one her? Also, another thing that is absent here is that, like, we can't just replace one word if another word is connected to it. Like, the name is connected to the pronoun. There's some names that, are, they're not, very few names you could say are on 100% androgynous, where it's 50 it's a coin toss. So we have to bunch them together, and that's what we're doing here with the baselines. So and we put in this template here, and it's doing it's going to run it several times and do that kind of exercise where it's comparing one to another and then averaging out the results. So we're comparing a mirror to all the baselines. And as you can see here, well, all the notions we had of Toronto being obscure, it was only obscure when compared to Vancouver, but in the vicinity of other cities, it's not really making much of a difference what city name we use. But and then when we put in throwing different names and we're pairing it with a pronoun, we're seeing that some of the biases that we thought were there, not that they don't seem to be there anymore, but some others are more. His is still very much connected to guitar and playing and watching and movies. Just no longer like as prominent with science and reading. So to make a conclusive test on bias, we would have to do a lot more than that, what we've done so far. But like there's a lot of different things can be done with this kind of test. So, or XAI method. So that's pretty